Hey guys, it's Miss Johnson and I'm here to bring you our fourth notes video for Unit 4. Today we're talking about special case factoring. So we've spent a couple days factoring expressions that are trinomials, learned a couple of different methods, and now we're going to look at some other special types of expressions that have some patterns to them, which is why we call them special cases. So the first one that we're going to look at is a difference of two squares. And what a difference of two squares is a binomial of two perfect squares that are being subtracted. So binomial, if we think about that word, that means we have two terms. If you look at that prefix, bi like bicycle, bicycle has two wheels, binomial has two terms. We need both of those terms to be perfect squares, and we know that they're being subtracted, hence the word difference. So this is called a difference of two squares because it's two perfect squares being subtracted. I know that the b term is 0x. My b term cancels out. What this means is the insides and outsides cancel out. They cancel each other, I should say. So my factored form is what we call the plus and minus pattern. You're going to have one positive and one negative of the same two factors. And you get those two factors by taking the square root of the first term and putting it in the first spot, and the square root of the second term and putting it in the second spot. So I could say that this is the square root of the ax squared, and that's the square root of c. That's the square root of ax squared, that's the square root of c. So that's going to be my factored form. One of them is added, one of them is subtracted. As with every other type of factoring that I do, I want to check for GCF first. So that has to be the first thing that I look for before I even get into the factoring piece. All right, let's try a few. If I look at number 1, I've got n squared minus 25. Now, I know that n squared is the same thing as n times n. And I know that 25 is the same thing as 5 times 5. And I know that I have subtraction in the middle, so that's a good thing. That's what makes this a perfect square, is that it's a number times itself. So square root of n squared is n. If I set up my factored form here, I have n in the first, I have 5 in the second, I have positive and negative, and plus 5 and minus 5. Now, if it helps you, if you'd like to check and make sure, always refoil it back. Just do the multiplication to see if you've got the right answer. N times n is n squared. Outside, n times negative 5 is negative 5n. Inside, that's positive 5n. And last, negative 25. Here's where that b term dropping out comes into play. I got a negative 5n and a positive 5n. Negative 5 and positive 5 cancels out. They cancel each other. That's 0n. So I'd have n squared plus 0n minus 25, but I don't need to write the 0n in the middle. That doesn't make any difference. N squared minus 25. That got me back to my original expression, so I know that that's my factored form. N plus 5, n minus 5. If I take a look at number 2, 36x squared minus 49y squared, I know that 36 is the same thing as 6 times 6, and x squared is the same thing as x times x. So this is really 6x times 6x. This one right here, 7y times 7y. That's the square root of those two. In the middle, I have subtraction. So I'm looking at 6x plus 7y times 6x minus 7y. If I refoiled those back, I get a big long expression here, but the first two would give me the 36x squared. The outsides would give me negative 42xy. The insides would give me positive 42xy. And the last would give me negative 49y squared. Now this negative 42xy and positive 42xy, they are like terms because they have the same variable parts. When you add them together, they cancel out. And you're back at the 36x squared minus 49y squared. So you know that that's your factored form. My factored form here is the 6x plus 7y times 6x minus 7y. And there I have it. Let's take a look at the next one. 48a to the third minus 12a. All right, there is a GCF here that you need to take into consideration. 48 and 12 have a common factor of 12, and a to the third and a have a common factor of a. So I'm going to take a 12a out and see what I have left over. If I pull 12a out, 48 divided by 12 is 4. A to the third divided by a is a squared. 12 divided by 12 is 1, and a divided by a is cancels out, is also just a 1. So I have 4a squared minus 1 left over. And this is a perfect square, subtraction in the middle. So I have that 12a GCF out front, and then I have the square root, which is 2a, and the square root of 1, which is 1. 2a and 1, one's adding, one's subtracting. Now, just like in our trinomials, I know that I can flip the order of those two. If you wrote it as 12a times 2a minus 1 and then 2a plus 1, it means the same thing. It does not matter what order you write those in, because multiplication can go in any order. So we're good there. Take a look at number 4. I have a GCF to factor out here as well. Now 9 and 4 don't have anything in common, but x to the third and x certainly do. So I can divide out an x here, leaving me with 9x squared minus 4 left behind. 9 is a perfect square, x squared is a perfect square. 4 is a perfect square. Subtraction in the middle. So I know I've got that plus and minus pattern. I know I have an x out front just from that GCF. So that's going to be a 3x plus 2, 3x minus 2, and that's my factored form. Number 5, check for a GCF. There's nothing in common between 64 and 1, and there's also nothing in common between g squared and h squared. So there's no GCF here, but I do know that 64 is a perfect square. That's 8 times 8. And I know that g squared is a perfect square, so I can make that 8g times 8g. H squared is h times h, so I've got all sorts of perfect squares going on and subtraction in the middle. So that's 8g plus h and 8g minus h. Now again, if you flipped the order of those two and wrote the minus in front, means the same thing. Okay, let's take a look at number 6. Number 6 gets a little bit trickier because, well, first of all, there's a GCF. Let's take that y out. There's a y to the third and a y. I'm going to pull it out front. Oops, not 4, sorry, y. So I have a y out front, and then I have negative 4x squared plus 9 behind. Now, this doesn't look like a difference of two squares because there's no subtraction in the middle. However, I have one negative perfect square and one positive perfect square. And if I flip that around and write that as 9 minus 4x squared, now it does look like a difference of two squares. So I can take the square root of the 9, take the square root of the 4x squared. That y GCF has to stay out front. So that's 3 plus 2x and 3 minus 2x. So that's one way that you could factor this. The other way that you could factor this is if I work with that one and I've got y times that negative 4x squared plus 9, this still is a difference of two perfect squares. It's just that my negative term is in the first position. So this is the one that I need to have be plus and minus. One of these is going to be a negative 2x squared, and one of them is going to be a, or not squared, sorry. One of them is going to be a negative 2x, and one of them is going to be a positive 2x. It's just that that negative term is the first term instead of the second. So it's still going to work, and then both of these are going to be positive 3 because I have a plus, so both are positive 3. Still have that y out front. You could have written it either way, but I think it's probably easiest if you just flip that negative term to the back so that you know you've got that plus and minus pattern. It's hard to wrap our brains around putting the negative in front and having the second term be positive for both. It just makes it a little bit trickier. But just know that that's the same expression. Those mean the same thing. they'll give you the same result, I should say. Okay, let's talk perfect square trinomials. So flip over to the back of your note sheet. Perfect square trinomials are, we're back at trinomials here. It's a trinomial in which the first and last term are perfect squares. Well, hello, there's the name. Trinomial. First and last term are the perfect squares. Not necessarily the middle. That may not happen, but the first and the last term need to be. The factored form gives you the same factor twice. It's the square root of the first term and the square root of the last term. And you add if the middle term is positive and subtract if the middle term is negative. And as always, check for GCF first. So we're going to talk about this, what we do with this middle term, because that's going to be the trickiest part here. So, but the key thing about a perfect square trinomial is that the factored form is the same factor twice. Let's take a look at number 7. So in 7, I have n squared minus 24n plus 144. So I recognize that this is a perfect square and that that's a perfect square. This is the same thing as 12 times 12. This is the same thing as n times n. I have a negative term in the middle. So if I set up my factors here, I know I want n and 12, n and 12. Since this middle term is negative, these both need to be negative. And always, always, always check to make sure that you FOIL it back to get the right thing. N times n is n squared. Outsides, n times negative 12 is negative 12n. Insides, negative 12n. And last, positive 144. That negative 12n and negative 12n is negative 24. So there's my original expression of that negative 24 in the middle, n minus 12, n minus 12. Now, that's one way that you could write this. Some people will also write this, or sometimes you'll see this on like an ACT or multiple choice test. You could write this as n minus 12 quantity squared. That is another way. If you have a power of 2 on the outside, that really just means you have 2 factors of the whole thing. Let's take a look at number 8. 9y squared minus 12y plus 4. That means I have a perfect square here, perfect square there, subtraction in the middle to get me that 12y. So if I take the square root of that, I know that the square root of 9y squared is 3y. Square root of 4 is 2. So 3y and 2. And again, I want a negative term in the middle, so these both have to be subtraction. So I end up, if I FOIL that back, that's 9y squared. Outside is negative 6y. Inside is negative 6y again. Last is positive 4. Negative 6y and negative 6y are negative 12y. So that's my factored form. 3y minus 2 and 3y minus 2. So you can see how we get the same factor twice, 3y minus 2, 3y minus 2, which is why we're also allowed to write it as 3y minus 2 quantity squared. You don't need to write both these answers for me. I don't care which one you show me. Either one will work. Number 9, 18y squared minus 48y plus 32. Now the first thing I recognize in this one is that they have a GCF. I know that I can take out a 2, so I'm going to do that first. So if I divide out a 2, I'm left with 9y squared minus 24y plus 16. And then I recognize that 9 is a perfect square. That's 3 times 3. So 3y times 3y. 16 is a perfect square, 4 times 4. And I can draw a line to remind myself to put the GCF back on, but I have 3y plus 4, 3y plus 4, quantity 2 out front for my GCF. Or you could write it as 2, 3y plus 4 quantity squared. You don't want to square the 2. We're not squaring the GCF. We're just squaring this piece in the middle. Last one of these, 50g squared plus 40g plus 8. So first thing I recognize, again, I have a GCF of 2, so I'm going to take it out. That gives me 25g squared plus 20g plus 4. So then I take the square root of that, take the square root of that. I want a positive term in the middle this time. So I have 5g plus 2, 5g plus 2 with a 2 out front. Square root of 4, that's 2 times 2. That's 5g times 5g. That's where I get those. Or you can write it as 2 5g plus 2 quantity squared and go from there. All right, last little piece for us to talk about, relatively prime expressions. Every once in a while, it doesn't happen all that often, but every once in a while, some expressions that we're given have no way to be broken apart. There's no way that you can take apart the multiplication here. Those expressions are not factorable. We have to make sure that we try all possible combinations and we still check for a GCF, but we call those expressions relatively prime. Relatively prime expressions are simply not factorable. There's nothing that we can do about it. So if I take a look at number 11, I'm going to go back to my X method that I used way back in lesson 2, just to kind of list out my options here. But if I look at number 11 and I want to factor that trinomial, I have a leading coefficient of 1. So if I set up an X, 1 times 9 gives me 9 on the top, middle term gives me 3. I want to give myself a product of 9 and a sum of 3. Well, what multiplies to 9? If I think about what multiplies to 9, 9 is 1 times 9 or 3 times 3. Those are my only options. If I add, this gives me a 10. Add here, this gives me a 6. None of those options are a 3. So I cannot do anything with this. This is simply relatively prime. And basically all that means is that they are prime relative to each other. They aren't necessarily all prime numbers, but they are prime relative to each other. So there's nothing we can do to factor it. Let's take a look at number 12. Now our directions here say factor the expression completely. So I still notice that there's a GCF of 5 and I have to take that out. So if I take that out, I get x squared plus 2x plus 2. And then I want to factor what's left. So this would be a product of 2 and a sum of 2. Well, the only way to get a product of 2 is if I have a 1 and a 2, which when I add those gives me a 3. So I can't do it. I can't do it. This is my factored form. Now, I could state that the inside is relatively prime, but the fact that I took a GCF out means that I still have a factored piece of the expression. So that's my factored form. The rest of it is relatively prime. I can't do anything with the inside, but I still want to list that GCF out front. Last one, 4x squared minus x plus 7. I want to multiply first and last. I get a positive 28 up here and a negative 1 sum. So let's think about what multiplies to 28. 28 could be 1 and 28, could be 2 and 14, could be 4 and 7. And I think those are my only options. There's no 3, nope, 5, nope, that's it. 1 plus 28 gives me 29. 2 plus 14 gives me 16. 4 plus 7 gives me 11. Even if one were negative, that would give me a 27. That would give me a 12 because I want a negative in the middle here. That would give me a 3. None of those options give me a negative 1. None of them work. Boop. So I have a relatively prime expression here. So you just have to exhaust all of your options. Make sure you check everything because sometimes there's a lot of combinations that are going to get you to that middle term. But if you've checked every single combination and you're sure there's nothing that can break it apart, then that's a relatively prime expression. All right, that's going to take us to the end of our notes 4 for today. Thanks for listening, and I will see you next time.